Okay, well, it's great to see so many of you here, and my name is Mark Hornick. I'm with the Advanced Analytics and Machine Learning Group out of Burlington, Massachusetts, just north of Boston. I'm here to talk to you today about architectural elements for enabling R for big data. Oracle Standard Safe Harbor Statement, I'm obliged to show. So when we talk about big data, we've heard a little bit about it so far at the conference, and sometimes it's positive, sometimes it's negative, but how many people here think they actually use big data? Is anybody here using big data? Okay, there are a few hands. Well, what do we mean by big data? Here I'm going to use the definition of big data is a term for data sets that are so large or complex that traditional data processing applications are inadequate to deal with them. So, what do we have to work with then for architectural elements supporting aspects of big data? The first is transparent data access and analysis and exploration. We don't want to have to change languages. We're here because we like R. We use R on a regular basis. Do we want to go to Python? Do we want to go to SQL, to other languages if we don't have to? I would say no. Scalable machine learning. How many people spend hours building models? And would it be nice if you could do that in seconds or minutes because your data is so large? How about data and task parallelism? How easy is it for you to actually craft and specify that I want to partition my data and load it into parallel R engines? Or finally, your data scientist does a lot of work to craft an R script that does exactly what's necessary with graphs and data, but then when you have to hand it over to application developers, how easy is it for them to incorporate that? Well, those are the types of problems we want to address. The first one here, transparent data access, analysis, and exploration. So if we look at the standard architecture for working with R, you have the R engine, the users interacting with it. You've got to pull that data into R in order to use it. Well, we know that the data has to fit. And as we've heard, with memories getting larger and machines more powerful, you can fit a lot of data, and R can often do a pretty decent job with reasonable sized data. But if that data gets a little bit bigger, you don't have that luxury. But perhaps the biggest problem is even if you can get the memory into R, how much time does it take to move that data from wherever it is into R? I'm going to show a data point a little bit later on that. So here's what we'd like to do from an architectural element perspective. We'd like to maintain the features of R. We really like the language, so we'd like users to be able to continue to use it, but offload the processing to powerful backends that were designed to actually manipulate data at scale, high-performance compute engines. These might be at a relational database. They might be Spark or Hadoop. And in terms of components, some of the things I'll highlight through this is what Oracle provides in this space is the Oracle Advanced Analytics, which Oracle R Enterprise, Oracle R Advanced Analytics for Hadoop in the Hadoop space, and as well as Spark. But then we also see examples with dplyr and perhaps Sparkly R that are also having flavors of these that you can address some of this. So I talked about how we're going to leave the data where it is, and one way of doing that is through proxy objects. So what we want to do is say we know what a data frame is, but in the case of big data, let's have a proxy that represents that data where it resides. In the case of the database, it's a very different structure that we're working with, as shown on the bottom. And in particular, it's focusing on having a query that corresponds to or points to that data. And we can actually stack these queries on top of one another through abstractions in R. So users just use R syntax. So let's give a few examples of that. You load the ORE library, Oracle R Enterprise. We connect to the database, and we can see what are the tables that exist. And these will show up as ORE frames, a subclass of data frame. But notice that the syntax there, the items in red are ORE frames, but this is all standard R syntax. We're using that, and this is being translated into SQL for execution at the back end of the database. But we've gone a little bit further, and coming in ORE 151, we're even expanding to dplyr, because it seems like dplyr is a very popular package. It's almost a part of R itself, so we're having that same abstraction layer there. And then graph analytics. Does anyone do graph analytics? Analyzing large networks? Okay, well, PGX is part of the Oracle Spatial and Graph, and that does very high-scale graph analytics, and you can see here just simple things of being able to take nodes and nodes and edges, materializing those into a graph, and then doing things like betweenness and page rank on those, and then putting those results back into the database where you may want to do further analysis on those. So that brings us to scalable machine learning. Again, the approach is load the data, do some processing in R, and then write out your results. Those results could be the models, it could be the scores that you're producing, any number of facets. However, we still have the scalability issue of how long does it take and how much data can I work with. So there are backends that are providing a lot of this functionality, parallel distributed algorithms, so we can offload the model building and scoring to these backends without impacting the client. We can also maintain the same R formula specification, because that's a very convenient way to characterize model building. And we do enable this with proxies as well. So whether we're at the database with useR or Spark or PGX for graph analysis or Hadoop, we have access to these back-end systems. Let's make this a little more concrete. So we've all used LM most likely. And I say, if you don't want to move the data, what's really the impact of that? Well, even if we can fit the data in memory, here we're using a 4 terabyte machine, so clearly there's no issue with memory. We have 220 gigabytes. It takes over an hour in this environment to pull that out of the database and bring it into R. Perhaps some of you have encountered delays of that sort. So what is the time for computation of the LM model itself? Well, on this machine, it took about 43 minutes. So that's our baseline, an hour and 43 minutes, that's 1x. Now, if we do the same thing with Oracle R Enterprise, the thing to note is the performance of the model build is about the same, but we've eliminated the data movement because the data is already in the database and the algorithm is working right there. So we already have a 2.5 times performance improvement. But let's go further. It's a parallel distributed algorithm. So with only 32 threads, we can bring that down to 1.5 minutes, and now you've got a 68 times improvement in the performance of that. So you can either reclaim that time to do something else or build more models, and that's really what we're all about. Now, on the Hadoop side, we can also claim that not all parallel implementations are the same, right? They might do well working on big data, but how well do they do that? So the comparison here is looking at the Oracle R Advanced Analytics for Hadoop LM algorithm against the Spark MLlib LM algorithm. So on the left-hand side, you'll see that, yes, we're 6 times faster, but you might say that's not a big deal. We don't really care about that timing there. But what's being illustrated is what happens if you constrain the Spark memory? How does the algorithm perform then? As you constrain memory more, we see that there's an exponential increase in the amount of time that it takes to compute that algorithm, and to the point where it won't even finish. So if you have many users hitting the same machine, this may have an impact for them. The same is true for the GLM that we benchmarked as well. So let's move on to data and task parallelism. And we had a very good tutorial on Tuesday that highlighted all the different ways that you can use parallelism in R. And so you're essentially handcrafting the spawning of R engines and feeding them data, loading that data into, say, the master and giving it to the workers. But we know that moving data can be relatively slow. And of course, it has to fit into memory. So what is an alternative to this? Well, instead of having the R engine controlled by the client, let's take the R function that we've written and let's put that to a backend that will manage all of this for us. So it will do things such as allow us to do data parallel and task parallel execution automatically. It will partition the data that we need and load it into our R functions that we specify, as well as to manage those R engines for startup and teardown. And of course, we'd want to use CRAN packages here as well. What's nice about this is that the client is optional. You can take it away, and you've eliminated one point of failure in your system. And since the database is typically supporting mission-critical applications, you can rely on it for being there to run your R code. Okay. And this is supported by the Oracle R Enterprise component. So what are some examples of how you can do this? Well, the first function I'll show is one part of the embedded R execution capability, where we have useR table applied. You see the first argument there, the iris table, that's an useR frame. So we're passing that in, we're saying, on the back end, I want you to take the R function, which comes next, and I want you to load the E1071, I want you to build the model, and I want you to save it in what we refer to as a data store in the database, as opposed to having to write it out to flat files. And of course, if you have many flat files, that's a management problem unto itself. Now, if I want to use that, I can again create a function that is going to allow me to score. So I load the E1071, I load the model from the data store in the database, and I return the score result. I also am going to define the form of that result, because I'd like that to come back in the form of a table, not a list of independently executed elements, and then I can see the results after that. The function ORE row apply takes the ORE frame, iris table, the function. We can specify where the data store is supposed to come from. How many parallel engines do we want to run this? All in a single function call. What the results should look like, and ultimately, in this case, how many rows do I want to process at a time? Here, 10, because iris is small, but you could imagine 1 million or 10 million rows, depending on what your customer requirements are. Talked about more data parallel capabilities. ORE group apply is going to allow you to identify a partition column or set of columns that you're going to use the distinct values to partition the data, and then feed each partition to one execution of that function, and the results can all be brought back, and you can see what the results look like there. Deployment is the last one, which I think is really crucial for so many organizations, even if you don't have big data, because when you got finished, whether you've got big or small data, it's still how are you going to get that in the hands of application developers and make it easy for them to uptake your work. So the traditional approach is, yes, you have your enterprise application. There are a myriad of tools that we can use to enable invoking R and getting results back. But another alternative is to say, what do enterprise applications typically use? What they typically use is SQL to interface with databases. What if you could take your R function, store it in the database, and use SQL to actually execute it? It would be very easy for you to then get your structured results, get your images, and have those brought up in the applications that are doing that. You could even schedule your R function for execution. Here are a couple of examples of what it looks like in SQL to do this. Now, I said you can store your R function in the database. Well, you can do that from R, but as shown here, you can also do that from SQL. So it's as simple as having a PL SQL script here that is providing your R function right there highlighted in red. But then you'll want to use SQL to invoke this and get those results back. So in the first case, we'll look at the select ID and image. So I've asked for the PNG images that are coming back. It shows up as a table with one row, and you can view that image as a PNG at that point. Or perhaps I use the next one and say, I want to get back the structured content to column table. This shows up as a table that you can join with other things or materialize as its own entity so it doesn't have to be computed again. And of course, last, you have XML, that I would like to take the XML that has both the structured content and the image content as one. So for architecture elements enabling R for big data, we're really saying that we want to leverage powerful backends to support this, have parallel distributed algorithms that we can work with, and then enable that parallelism easy for big data processing. Most important is to have the data scientists' work be able to be consumed immediately and easily by enterprise applications. So just to give you a little highlight of the tools themselves, so Oracle R Enterprise is taking advantage of the database as a high-performance compute engine and providing these machine learning algorithms at scale, also allowing you to store these objects in the database and integrate our results into applications. We often get asked, well, what algorithms do you support? Well, these are a set of the parallel distributed algorithms that are available in the database, whether you're dealing with SQL or R or a user interface that we provide through SQL Developer. I talked about graph and the importance of that. This is just a listing of some of the functions that are available through the parallel graph engine, PGX, also associated with the spatial and graph option itself. On the Hadoop side, we have the Oracle R Advanced Analytics for Hadoop. So it's giving you this ability to have transparent access to HDFS data, and it will translate the R invocations into HQL to allow you to work with that. It also has its own set of parallel distributed algorithms. That might help. Okay, I'll finish quickly. That's a warning, right? The open source R mappers, so you can write Okay. So you can write your mappers and reducers in R and actually leverage CRAN packages in combination with that. And in the case of the Oracle R Advanced Analytics for Hadoop with 2.7, a range of algorithms that are, some that are still Hadoop-based, more that are Spark-based. As people said, you got to talk about neural networks. Well, we have deep neural networks. You can specify arbitrary number of hidden layers and nodes and a wide range of activation functions on that. So try it out sometime if you get a chance. But also Spark MLlib. We've incorporated a number of those algorithms because they're quite popular. But we give the same standard interface that we do to all of the algorithms at that level using the R syntax for that with a formula statement. So with that, I would like to thank you for your attention and say if you'd like more information, you can go to oracle.com/go/r or stop by the booth and I'll be happy to give you a demonstration of ORE and talk further with you. So thank you very much.